Hi pre-calculus students. These video notes are on a review of polynomial functions. So first of all, I want to go over what our standard, and let me just say that all of this should be things that you learned last year in Algebra 2. I'm going to kind of run through a lot of big ideas, and you're going to have a chance to practice in class next time. So first of all, we have the standard form of a polynomial function. Which looks something like f of x equals a sub n times x to the nth, and we kind of have a series of terms that looks like this all the way down to a sub 1 times x plus an a sub 0, which is just like our constant term. So in this setup here, we have a must be a real number, and our exponents are all going to be integers. Okay. So then another kind of, a little bit more vocabulary here. We have the leading term of a polynomial would be the term with the highest exponent n. Okay, so it is our a sub n times x to the n. And this isn't always necessarily going to be your first term that you see, but it needs to have the highest exponent. And then another vocabulary is we call the leading coefficient, which would be, well, look at your leading term. The leading coefficient would be the coefficient of that term. In this case, we'd write it as a sub n. And then we also have something called the degree of the polynomial, which is exactly just the value of that highest exponent. So we would say our degree is n. Okay, so now we got some vocabulary out of the way. Just want to kind of talk about some patterns we notice as we start graphing these functions. So if we start with like n equals 1, that would be something like, the most basic form would be like f of x equals x. And if we just kind of sketch a quick graph, we know this is linear, so it looks something like that. When n is 2, the most basic form of the polynomial would just be the one term x squared. And if we sketch a graph here, we know it looks like a parabola. Yeah, something like this. And there's a reason I'm kind of running through this. I'm just going to kind of do so quickly. So now we have x cubed. Looks something like that. When n is 4. Now for this one, you may or may not know what x to the 4th looks like when you graph it, but it almost looks exactly like x squared, except that you kind of have it's a little bit flatter around the origin, because when you raise like decimals, like between -1 and 1 to the 4th power, it's going to give you something slightly smaller. It's going to give you something smaller than when you just square them. So it ends up looking flatter. And we'll do one more. We'll just do n to the 5th, which would be f of x equals x to the 5th. And again, it's going to end up looking something like x to the 3rd, except again, it's going to be flatter around the origin. And so this kind of pattern continues, and what you'll notice is all of the odd functions, so when n is 1, when n is 3, and when n is 5, so when I'm saying odd functions, I'm sorry, what I really mean is when n is odd, we see on the left-hand side our functions going down, and on the right-hand side our functions going up. And for all of the values when n is even, we see it's going up on both ends, okay? And this has something to do with what we're going to call our end behavior, right? What's happening to our function as x is really, really negative or really, really positive. And this leads to kind of this pattern of if n is odd or even, it's going to change our end behavior, okay? One other thing I want to quickly mention before I talk about end behavior is if I'm thinking about kind of like these most basic versions of the function, then my transformation rules that we learned last year and we talked about in our exponentials unit still apply. So if I gave you a function that looks like f of x equals, say, negative x plus 1 to the 4th power, you could say, well, I know that this plus 1 is going to be a shift left, and this negative out front is going to be a reflection over x, right? So you could imagine kind of taking this version of the graph and doing these different transformations. And so I need to shift it to the left one, and I need to reflect it, so maybe it looks something like that, okay? So that's one thing to kind of keep in mind. So now I'm going to talk about end behavior. And so we're actually going to think about end behavior this year in terms of limits. So end behavior is one way of thinking about it is what's happening on the left and the right side of your graph. So instead of thinking left and right, we're going to think the limit as x goes to negative infinity and the limit as x goes to positive infinity. And it depends on two things. It depends on the degree being odd versus even, right? That's going to change the way the graph is pointing. But it also depends on if there's like a reflection or not, right? Because if n is even and there's a reflection, then the two sides facing up are going to be now facing down, right? So this leads us to a little chart we can draw. And I would say try to make your chart as wide, as big as you can. I am a little bit limited in space, but try to make it kind of wide as your page. And there's going to be 4 boxes. And along the top, we're going to put the degree. So the degree we want to think about as being either odd or even. And again, degree, we're talking about n. And then along the side in these 2 squares, we want to think about what is the leading coefficient doing? Because if this negative sign out here is going to impact the leading coefficient. And in that case, we need to think about, is the leading coefficient positive or negative? Okay? And we want to see how will each of these impact the end behavior of the function. So in each of these squares, I'm going to draw a little coordinate plane, but I want to leave a little bit of space. Okay, so in the first one, we're saying odd, and our leading coefficient is positive, so it should look something like any of these odd functions, right, at the end. So certainly it's got to be going down on the left and up on the right. Now, if it's not necessarily always just looking exactly like those other functions. So there could be some sort of like curve happening in the middle, but these ends are always going to stay the same. So then how would I describe this end behavior? I would say the limit as x goes to negative infinity of f of x equals, well, on the left-hand side, as my x values go to negative infinity, my y values are, my arrow is pointing down. My y values are also going to negative infinity. And the limit as x goes to positive infinity of f of x would be positive infinity because my arrow is going up on the positives when x values are getting larger. Okay, so now if I think about what happens if my leading coefficient is negative, but I still have an odd function, essentially my graph is going to flip over the x-axis. So now on my left-hand side, it's going to be going up, and on my right-hand side, it's going to be going down. And again, I don't know exactly what it's looking like in between. So then essentially what's going to happen with my limits or my end behavior is they're just going to flip-flop. So now the limit as x approaches negative infinity, that's over here, now my y values are approaching positive infinity. My limit as x approaches positive infinity on the right-hand side, now my arrow is pointing down. So now I have a negative infinity down here. Okay? So now we're going to do the same thing with the even functions. So the idea here, again, I should know if it's even and positive, it should again look like one of these two, right, with the arrows both pointing up at the ends. And I'm not exactly sure what's happening in between, but something like that maybe. So my limit as x approaches negative infinity of f of x, well, it's pointing up, so that means positive infinity. My y value is approaching positive infinity. The limit as x approaches positive infinity for f of x, my y values are also going up on the right-hand side. So this is also positive infinity. Okay, and then last one. Here, now everything's going to flip if my leading coefficient is negative. So maybe something like this. Limit as x goes to negative infinity of f of x is now negative infinity down here. And the limit as x goes to positive infinity, that's over here, is also negative infinity. Okay, so this kind of chart is going to become important when we're kind of looking at a function and trying to decide its end behavior. It's always useful to kind of sketch one of these graphs, and then the end behaviors should reveal themselves to you. Okay, so next page of our notes. Okay, so I now want to get into a little bit more about the factored form of a polynomial. It looks something like f of x equals a times x minus r, and I'm going to put r1 here, to the p1, where p is some exponent. And then we could have x minus r2 to some other exponent, and we kind of have as many factors as there are in this function. Okay, so the key kind of understandings about this form is it reveals the zeros or the roots of the polynomial. So a couple of things we can say here. We would say any of the x minus r's, this is a factor of f of x. And then we would set, we could also then, if we have factored form, we could set each factor equal to 0, and we could find the zeros of the function. So we would also say x equals r sub I, and I'm just using I to represent any of these r values, is a 0 of the function, because it would be where y is 0. We also call it a solution, because it's a solution of setting the equation f of x equal to 0. And we can also say that this is giving us the x-intercept, right? We could also say r sub I, or one of the x-intercepts, comma 0 is a x-intercept. And this becomes very important when we are trying to sketch a graph of a polynomial. It is really important to know where are the x-intercepts so that I can get a more accurate graph. So we're always going to want to try to get it into factored form in order to do that. And we have a bunch of different strategies to do that we're going to be reviewing in this unit. I'm not going to get too much into that right now. So for right now, we're just going to think about relying on factoring. So just as a quick example, if I have something like f of x equals negative 2x to the fourth minus 2x squared, and I wanted to find the factored form, what I could do is, okay, how do I factor this? I could factor out a GCF, which is negative 2x squared. What's left is x squared minus 1. That factors further. And then each of these factors is giving me a 0. So technically, this right here is the same thing as saying x minus 0 squared, right? If I'm thinking about this form. So what are my zeros? My zeros would be x equals 0. And then from x plus 1, if I set that equal to 0, I get x equals negative 1. And then from here, I would get x equals positive 1. Okay? And this is all going to become important when I go to try to graph the function. So quickly, we're going to just look at the steps to graphing. So I'd always want to know the y-intercept, which should be very easy to find, especially if I have standard form, it's always going to be that like a sub 0 term, or I can always plug in x equals 0 and get the point where on the y-axis where x is 0. Okay, so the other thing that's going to be important is going to be our end behavior. I'd like to know what's happening on either end of my graph. Next is going to be the zeros, and I also need to think about something here called multiplicity, which is if my zeros are repeated or not. And it's going to matter if it's odd versus even repeats. Odd number of repeats means you're going to cross the x-axis. And an even repeat means that you're going to kind of bounce off the x-axis. So then the last step would be to sketch the curve. And sometimes we'll like plot some points in between. So if I was doing this for the function above that I already found the zeros for, so that's negative 2x to the fourth minus 2x squared, what I'd have to do is say, okay, what's my y-intercept first of all for this example? Well, it has no a sub 0, so then my y-intercept must be 0, 0. My end behavior. So I don't necessarily, if I'm just graphing, I don't necessarily need to write my limit notation end behavior. I just need to think my leading coefficient is negative and my exponent n is even. So what should this look like? It should look something like this at my endpoints, right? Okay, my zeros, we already had my zeros up above, so I have x equals 0, x equals negative 1, and x equals 1. Now the only thing here is that the multiplicity for 0 is actually 2 because it gets squared, right? So my multiplicity is going to be 2 here, but for both of these it's going to be 1, right? Which means that I'm going to cross the x-axis at these points, but bounce off the x-axis at this point. So when we go to put this all together, I need to make sure I'm sketching, kind of having the right number of x values to get to all my zeros. So I just need 1 and negative 1. And I'm going to start by doing I'm going to plot my y-intercept at 0, 0. I also know I'm going to go through both of these points because those are my other two zeros. And I'm going to start with my end behavior. So I know it should be kind of coming from down here and ending over here. And now I can start kind of approaching my two first 0. And what's going to happen in each of these? Well, the multiplicity is 1, so I'm going to keep going through it. Right? And now I have to think, well, I have to get back down to this 0. So I got to turn. But once I get here, because my multiplicity is 2 at 0, I'm not actually crossing over, but I'm coming back up. And now I need to turn once more to get to my other 0. And this would be some rough sketch of this function. Okay, so you're now going to be practicing some more of these same skills, and we'll be building on this next week in class.